Okay, welcome to the lectures of Power System Dynamics and Control course. So last class we're about to start the time constants and the reactants and the subtransient and transient reactances because these are very essential for representing the model in terms of subtransient and transient reactances and open circuit transient and subtransient time constants. So, because this is as per the industry standard, so let us see how these parameters we can derive for a machine, for a synchronous machine. So, we have started this, in fact, in the last class. So, today we'll see in detail how we can derive these subtransient and transient reactances and also the open circuit subtransient and transient time constants. So synchronous machine parameters actually it is essential to represent the voltage equation and flux linkage equations in terms of subtransient and transient reactances, open circuit subtransient and transient time constants because the parameters of the industry grade synchronous generators are given in terms of the above parameters. So whenever we get a practical generator from industry, they provide these parameters. And whenever we do modeling of any synchronous machine or any induction machine, whatever, we consider those parameters. Considering those parameters, we can write the equations to model the machine. So let us first talk about subtransient and transient reactance. So I told that for in order to find the subtransient reactance, let us assume a voltage is applied at the stator terminal with all other rotor circuits are circuited. Okay, so at the stator terminal we are applying a voltage, and such that the current ID flows then immediately after the voltage is applied at t equal to 0 plus, the flux linkages psi FD and psi 1D will be 0. So now we'll consider the d-axis equations. We are not at all worried about the q-axis equations now. So we'll now consider only the d-axis equations, flux linkage equations. So let us write those equations. So d-axis flux linkage equations. So psi d, we know this is the stator flux linkage equation. That is xd into minus id, xmd ifd plus xmd I1d. Similarly, psi fd, we have written xmd minus id plus xfd ifd xmd I1d, psi 1d equal to xmd minus of xmd id plus xmd ifd plus x1d I1. So already we have derived these equations, and so initially we are with this initial condition we are assuming, because this is the subtransient condition, as soon as the voltage is applied, that means the switch is made on. So what will happen? Your psi FD and psi 1D will be 0 initially, right? And now from these two equations, and of course we have to substitute xFD equal to xLFD plus xMD, and x1d equal to xl1d plus xmd. So now substituting these parameters in these equations, these two equations, and again, I told in the last class, again by just eliminating I1d once, we'll find IFD, and again by eliminating IFD, we'll find I1d in terms of ID, right? That is what we'll do here. Let us do that. First, if we'll eliminate I1d from these two equations, from this equation and this equation, then we can write IFD in terms of ID, right? All these parameters are constant, right? So xmd xl1d by xmd plus xlfd plus xmd xl1d plus xlfd xl1d, right? Now if I'll eliminate IFD from these two equations and I'll express I1D in terms of ID, then you can do it in your home also as part of this course. You can try to do. When you'll eliminate IFD, you will find I1D in terms of ID, just multiplied with some constant terms, XMD, XLFD divided by XMD, XLFD plus XMD, XL1D plus XLFD, XL1D, right, into ID. So now we'll substitute this IFD and I1D equation in the first equation, which is written in terms of ID. Okay. So now if we'll substitute this IFD and I1D in the first equation, we'll find the side equation, that is side equation will become completely, it will be written in terms of ID, right? So this is the whole constant reactances and into ID. So that is nothing but minus of xt minus xmd square into xlfd plus xl1d divided by xmd xlfd plus xmd xl1d plus xlfd into xl1d. Yes. Now let us substitute xd equal to xls plus xmd. So xls is your leakage reactance and xmd is your mutual reactance. Now substituting this here in this equation, what you will find? Now just substituting and little bit doing some manipulation, we'll find this expression for side. Side will become equal to minus of xls plus xmd xlfd into xl1d by xmd xlfd plus xmd into xl1d plus xlfd into x1d. Now what we'll do, we'll bring this numerator term to the denominator by dividing it in the denominator term. We'll see it will become minus of xls plus 1 by 1 upon xmd plus 1 upon xlfd plus 1 upon xl1d into id, right? And hence I can write this as, because we generally write flux linkage equation as Li. So therefore L in per unit is equal to, of course, in reactance. So therefore I can write this as your reactance under subtransient condition. So reactance under subtransient condition is this. So that I can represent as xd double dash. Okay, that is d-axis subtransient reactance will be minus of xd double dash into id. So xd double dash is nothing but is equal to xls plus 1 by 1 upon xmd plus 1 upon xlfd plus 1 upon xl1d. So now we must understand these terms. This is your leakage reactance of the starter. This is your mutual reactance, okay, MD, okay, in the d-axis mutual reactance. And it is, of course, same for the between starter and between starter and rotor, right? And XLFD is your leakage field reactance, leakage rotor reactance of the field, right? It is across the d-axis. Similarly, XL1D is your leakage reactance in the corresponding to the damper winding, right? 1D damper end. So likewise, we considering the d-axis flux linkage equations, we derive the subtransient reactance, d-axis subtransient reactance. We can also by considering the q-axis flux linkage equations, we can derive the q-axis subtransient reactance, that is xq double dash. So just we need to assume that we are applying a voltage in the starter and assuming that IQ is flowing, and we'll again, by considering those equations, we'll find XLS, XQ double dash, that is Q axis subtransient reactance will become equal to XLS plus 1 by 1 upon XNQ plus 1 upon XL1Q plus 1 by 1 plus 1 upon XL to Q. So these are the two Q-axis damper winding leakage reactances, and this is your Q-axis mutual reactance, right? And this is your leakage reactance of the starter. Okay. So now these terms are clear. Now we derived D-axis subtransient reactance and Q-axis subtransient reactance. Okay. Again, we need to derive the open circuit time constants, open circuit subtransient and transient time constants. So for deriving the equations for transient reactances, the same logic can be. Okay. So before moving to the time constant, let's derive the transient reactance. These are the subtransient reactances. So for deriving the transient reactances, same logic we can apply with an additional assumption that the damper winding transients settle down faster as compared to the field winding transients. Hence, I1D can be assumed to be 0. So in all the flux linkage equations, we'll assume, considering the above assumptions in the subtransient reactance derivation, we can again assume that I1D is 0 under transient condition. Under transient condition, the damper transients are gradually, it dies out. So only the transient in the field winding remains. So therefore, we'll consider only the field winding transients. The damper winding transients will consider 0, right? In Q-axis also, we'll consider only the transient in the 1Q damper winding, not in 2Q damper winding. Okay. So so by assuming I1D is equal to 0 and considering these flux linkage equations, again we can derive the relationship between flux linkage and the current ID. Okay. So after deriving the equation, we'll find the expression as xd minus xmd squared by xmd plus xlf. Again, substituting xt equal to xls plus xmd. So we will substitute xt equal to xls plus xmd here in this equation. We'll find the equation as xls minus xls plus xmd into xlfd by xmd plus xlfd. It is wholly multiplied with id, right? So then just by taking this numerator term to the denominator, we'll get, just dividing it, we'll get minus of xls plus 1 by 1 upon xmd plus 1 upon xlfd into id. So that is equal to minus of xt dash id. So this whole term is xt dash, that is transient reactance, d-axis transient reactance. So I can write the d-axis transient reactance, that is xt dash, will be equal to xls plus 1 by 1 upon xmd plus 1 by xlfd. Okay. So now we can, similarly we can derive xq dash. So xq dash I can derive in the same way. I can write xls plus 1 by 1 upon xmq plus 1 upon xl1q. So only 1q term will be considered, right? So I1q is considered not equal to 0. So I2q will assume at 0 under transient condition. Again, we'll derive, now we have derived the subtransient and transient reactances, right? Now we'll derive the open circuit subtransient and transient time constants. So how we'll do it? So for finding the subtransient open circuit time constant, a voltage is applied to the field winding with the starter terminals open circuited, so that ID is 0. Okay. So in order to find this open circuit time constants, what we need to do, we need to open circuit the starter terminals, right? And a voltage is applied to the field winding. Okay. With the starter terminals open, So ID becomes 0 in this case, right? So now let us write the voltage equation first. So if we write the voltage equation, I can write VFD, that is D axis field winding voltage equation. VFD will be equal to RFD IFD plus 1 by omega base d psi phi d by dt. Then I will write the 1D axis voltage, that is V1D, will be equal to R1D into I1D plus 1 by omega base d by dt of psi 1D. Okay. So this is your voltage equation because we are assuming ID equal to 0, therefore the ID terms will become 0. From the flux linkage equation, your psi FD will be XMD minus ID plus XFD IFD plus XMD I1D, and your psi 1D is XMD minus ID plus XMD IFD plus X1D I1D. So now substituting ID equal to 0 in these two equations, what we'll get? We'll get, and also it's immediately after the voltage is applied, that is at t equal to 0 plus, the flux linkage psi 1D will become 0. So just by substituting here psi 1D equal to 0 here, and this terms is 0, then I can find I1D in terms of IFD. So IFD in terms of I1D. So IFD I can write minus of X1D by XMD into I1D. And again, just by substituting this IFD equation in in the V1D equation, so I'll write this, right? So in the V1D equation, in this equation, if I'll substitute here VFD, in the VFD equation, if I'll substitute IFD, then I can write, now this is V1D equation, okay. So in the V1D equation, I have to substitute 1 by omega base into your V1D equation is this 1 by omega is psi 1D. So psi 1D equation I have to substitute in V1D equations. Okay. So after substituting psi 1D equation, your equation will become like this. So it will become 1 by omega base XMD d IFD by dt plus X1D into d I1D by dt plus R1D I1D, right? That is equal to V1D, which is equal to 0. Now, if we'll substitute IFD here, okay, so now if we'll segregate this equation, 1 by omega base d IFD by dt, it will be equal to minus 1 by omega base X1D by XMD into di1d by dt minus r1d by xmd into I1d. So from this equation, we'll get this, right? So next, what we received, we got these two equations, right? Now we got this equation. Now we'll write VFD equation. So VFD equation is nothing but, so we want to express the VFD, that is because the voltage is applied in the field winding, and V1D is 0 in fact in the damper winding, and we want to express VFD equation in terms of I1D, right? So how we'll express it? Let us see. So VFD equation, we know VFD will be equal to RFD into IFD plus 1 by omega base d psi FD by dt, that is equal to, again I can write in case of IFD, I can substitute X1D by XMD I1D from the previous equation, right? So I can write minus RFD into X1D by XMD I1D plus 1 by omega base d by dt of, in case of psi FD, I can write XFD IFD plus XMD I1D because ID is equal to 0. So only these terms will remain, right? So now expanding these terms with respect to the derivatives, I will have minus RFD x1d by xmd into I1d plus 1 by omega s dIFD by dt xfd plus 1 by omega s di1d by dt into xmd. So now this term, we have an expression for this term, which is here, right? Now if I substitute this expression, that is here, minus 1 by omega base x1d xmd by xmd into di1d by dt minus r1d by xmd into I1d. If I substitute here in this equation, now your equation will look like this, right? Now just doing little manipulation, considering the terms of I1d separately, and of course 1 by omega base terms are separately, just separating the terms. Now what we'll find, the differential terms and the algebraic terms, you can see. So just segregating the algebraic terms separate and the differential terms separate, we'll find this expression, that is VFD will become equal to RFD x1d plus XFD R1d by XMD into I1d minus 1 by omega base xfd x1d minus xmd square by xmd into d by dt of I1d. Now we can see VFD is expressed completely in terms of I1d, right? Now, with little assumption that because we know that x1d is less than x1d is less than xfd always. It is quite less, right? Because this is your reactance of the field winding, this is reactance of the damper winding. So, of course, in the damper winding, of course, the damper winding reactance is very less. And here we can see RFD into X1D is very less than XFD into R1D because these resistance values are very less as compared to the reactance values. So therefore, we can say that RFD into X1D will be very less as compared to XFD into R1D, right? So therefore, what we'll assume here that this is less. So therefore, your RFD X1D plus XFD R1D can be written as XFD R1D. Okay, so this term I can neglect because this is very less as compared to this. So approximately the whole term will be equal to XFD into R1D. So now I can write it as VFD will be equal to XFD R1D by XMD into I1D minus 1 by omega base XFD X1D minus XMD square by XMD into d by dt of I1D. Okay. So now we can see this is a differential equation where we have a source VFD and it is written in terms of current I1D, right? Now, if we'll say that this is your one RL circuit, then this will represent your L, this will represent your R, right? Okay. Ri L di by dt, right? So therefore, I can write the time constant as L by R, right? So what I'll do, I'll divide this L term with R term. So now I can see, if I'll divide, I'll find the expression TDO double dash, that is subtransient reactance. So open circuits d-axis subtransient time constant will be just dividing those two terms, we'll get this term 1 by omega base R1D XFD X1D minus XMD square by XFD. Okay. So now we'll just little bit expanding and substituting XFD as XLFD plus XMD and X1D as XL1D plus XMD. Now I just little bit XFD also I have segregated. Now just expanding, multiplying and cancelling the terms, we'll have these terms remaining. Okay, and it with of course 1 by omega base R1D will remain as it is. Now just taking XL1D common, I will have xmd plus xlmd, which will cancel out, and therefore I will have xl1d plus 1 by 1 upon xmd plus 1 upon xlmd. So now this is your time constant. Open circuit dx is subtransient time constant, right? So this whole term is open circuit subtransient dx is time constant. Okay. So now similarly, I can, considering the q-axis equations, voltage and flux linkage equations, I can derive, of course, q-axis open circuit subtransient reactance. Open circuit q-axis subtransient reactance, and that will be equal to 1 by omega base R2Q into XL2Q plus 1 by 1 upon XMQ plus 1 by XL1Q. Right? So this is how we derived the subtransient, open circuit subtransient d-axis and q-axis time constant, right? Now let us derive the time constant, transient time constant. So this is your subtransient time constants. Now let us derive the similarly open circuit quadrature axis subtransient time constant in seconds can be expressed as this. Okay, this is what we have seen, right? Now we can also derive the transient time constant. For finding the open circuit direct axis transient time constant, along with the assumption taken for computing this, the subtransient open circuit subtransient d-axis time constant, the current in the damper winding, that is I1d, is assumed to be 0. Okay, so by assuming I1d, similar assumption we will consider what we have considered for deriving the transient reactances. Okay, similar assumption we'll do here, that I1d, the transient in the damper, will be die out during the transient condition when where field winding transients are considered, right? So therefore I1d is assumed to be 0. Now considering all the d-axis equations, so psi 1d will be, sorry, psi fd, I can write x fd ifd, because id and I1d both are 0. So it will have only one term, that is x fd ifd. Similarly, vfd, I can write rfd ifd plus 1 by omega base x fd ifd derivative of ifd. So other terms will be 0. Now from this equation, of course, very easily I can find the open circuit d-axis transient time constant, right? So that I can find easily from this equation. If we'll consider this voltage equation, I can easily find it out. So TDO dash will be equal to XFD by omega base divided by RFD. Okay, so this will be your open circuit transient time constant, d-axis transient time constant. Similarly, I can write the open circuit q-axis transient time constant as this. Okay, so it will be TQ dash will be equal to x1q by omega base into R1q. Okay, this is what we derived all the time constants and all the reactances, subtransient and transient reactance. Now what we'll do is that we'll, considering the equations of these constants or these parameters, we'll try to write the equations of voltage and flux in terms of these parameters. So that is a little bit difficult in order to manipulate, but we do that. Okay. Also, along with this, we'll define few new variables, that is EQ dash is equal to XMD by XFD into psi FD, and ED dash is equal to minus XMQ X1Q into psi 1Q. EFD will be equal to XMD by RFD into VFD. So these are the, wherever we'll find these terms, we can substitute this in like using EQ dash, and wherever we'll find minus xn cube by x1 cube into psi 1 cube, we can substitute ED dash, and similarly for xmd, RFD, VFD, we can substitute EFD. So in order to simplify the equations, we need to substitute these parameters along with other parameters. So like we'll find the equations in a simplified manner, considering EQ dash, ED dash, EFD, and your time constants, like your reactances, subtransient and transient reactances, XQ double dash, XQ dash, and TDO double dash, TDO dash, TQ double dash, TQ dash, and these parameters like EQ dash, ED dash, and EFD. So we'll see our equations all having these parameters only, which is actually provided by the machine manufacturer. Okay, the industry grade electrical machine and manufacturers. Okay. So in order to uh, find those equations, let us first see that this XFD, the equations of XFD and X1D. So considering the equation of XFD and X1D, we can write the equation of XFD and psi FD and psi 1D in terms of in the matrix form, right? So I can write XMD into ID plus XFD, XMD, X1D into IFD by I1D. So in the matrix form, we can write this. And in order to find out IFD, I1D from this equation, I will just take the inverse of this matrix and multiply throughout the equation. So I'll get this equation, right? So it will give me IFD and I1D. So just segregating and finding the equation individually for IFD and I1D, I can write the equation for IFD as 1 by determinant of this matrix by, and also into the adjoint of this matrix, right, into ID, right? Similarly, all these terms are added, right? And this 1 by delta is nothing but this is your determinant of this matrix. Okay. Similarly, I can find the expression for I1D, which is equal to 1 by determinant of this matrix and or all other terms like adjoint of this matrix multiplied with this, adjoint of this matrix multiplied with this, right? We'll get this equation. So for above equation, we'll find x1d psi FD minus xmd into psi 1d plus x1d xmd minus xmd square into id. For the second equation, we'll find minus xmd psi FD plus xfd psi 1d plus xfd xmd minus xmd square into id. So now we can see these equations are in terms of ID only, right? And of course, other parameters are there, right? And this is your determinant. Okay. Now this is your determinant completely except dx1d minus xmd square. This is your determinant, right? Now a little bit expanding this just by substituting here xfd equal to xlfd plus xmd and x1d is equal to xl1d plus xmd. Just substituting here, I will find this expression, that is xlfd, xl1d plus xlfd into xmd plus xl1d into xmd. Okay. So this is your equation. Now, this is the equation for the determinant. Now, what we'll do is 1 by determinant of x1d psi fd. X1d psi fd here we'll eliminate from this equation, right? So if we'll eliminate, we'll find this expression. Okay. So it will become xf dx1 dy by xmd determinant xmd by xfd into psi fd. Okay. Psi fd. Okay. Okay, we'll see this from this we'll see in the next class. We'll maybe stop here, okay, and we'll continue in the next class. Okay. Thank you very much.